So generating functions are a very useful tool in discrete probability and discrete stochastic processes, and this little video will explain the basics. So the first thing is that a generating function, you have a generating function of a sequence of real numbers. So here's the definition. If A is a sequence of real numbers, A0, A1, A2, an infinite sequence, then the generating function is the following. We write G sub A of S, it's A0 plus A1 times S plus A2 times S squared, and so on. The nth term is AN, the nth term of the sequence, times A to the nth power. And then we can write it here in summation notation. Okay, so this is the definition. Let's see some very simple examples. What's the simplest sequence we can think of? A is just the sequence A0 equals 1, A1 equals 1, A2 equals 1, and so on. So let's write out the generating function. We have 1 plus 1 times S plus 1 times S squared plus dot 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 dot. And so this, if you recognize this, this is a geometric series, so we can actually write the generating function in closed form. And this is 1 over 1 minus S. And then I've written here for absolute value of S less than 1, sort of this closed form only makes sense when S is not too big. Okay, let's look at a slightly more complicated example. Now we have the alternating sequence. A0 equals 1, A1 equals minus 1, 1, minus 1, 1, minus 1, and so on. Okay, we can write out what generating function is now. It's 1 plus minus 1 times S plus 1 times S squared plus minus 1 times S cubed, and so on. And again, this is a geometric series, 1 over 1 plus S. Okay, so now you're starting to get the idea. These are simple examples. Let's look at another one. The alternating sequence 1, 0, 1, 0, 1, 0, 1, 0. So this is the same sequence that we saw before, except the odd terms disappear. So let's see what we have. So here we have 1 plus S squared plus S to the fourth plus dot dot dot. This is also a geometric series, and the closed form is 1 over 1 minus S squared. So that's fine. So you can see that only the even terms appear. Okay, so now let's start to do some stuff with generating functions. So for probability, a useful operation between two sequences of numbers is a convolution, and we'll see that. We've seen that before, actually, with characteristic functions. So let's look at this. The convolution of two sequences, A and B, where A is A0, A1, A2, B is B0, B1, B2, etc., is a sequence C. So the convolution of two sequences is another sequence, and the nth term of this C sequence is the sum of A0Bn plus A1Bn minus 1 plus dot 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 An B0. So it's the sum of all the terms whose indices add up to n. Okay, and what do we write? We write the sequence C, that's the convolution of the two sequences, is A star B. Okay, so here's a little useful exercise to do on your own. The convolution, the generating function of a convolution, this is spelled incorrectly, is the product of generating functions of the two individual sequences. So the generating function of this convolution A star B is the generating function of A times the generating function of B. And this is good to do on your own, this calculation. So let's see. Okay, so let's do an example. Let x and y be independent Poisson random variables with mean mu and lambda. What is the distribution of z, which is the sum of these two independent Poissons? So we've seen this a couple times before. We've done a calculation that proved that this is in fact another Poisson. But how can we do this with generating functions? So one way to see it is that the probability mass function of the sum of independent random variables is a convolution of the probability mass function. So here is the probability mass function of the sum. These are the individual probability mass functions. you can think of probability mass functions as of a non-negative integer random variable as a sequence of numbers. So the probability that z equals 0, the probability that z equals 1, the probability that z equals 2, and so on. So let's do a calculation. So let's have our sequence be the probability mass function of this Poisson random variable x with mean mu. So what is the generating function of the probability mass function? Just by definition, it's the probability that x equals I times s to the I, sum from I equals 0 to infinity. And we can just do this calculation. Let's see. So this is, we can pull out the e to the minus mu. Let's see if I can write this. E to the minus mu. And then we have sum of mu times s to the I power over I factorial. This you should recognize as the exponential power series. So this is e to the mu times s. So this equals e to the minus mu times e to the mu times s. And this equals e to the mu times s minus 1. And, oops, that should be a mu. Okay, so good enough. Right, and so if the probability mass function of a sum of independent random variables is the product of the probability mass functions of the summons, then we have, right, so we have fz equals fx convolution with fy. So the generating functions multiply. So we have generating function of the probability mass function of z equals e to the mu s minus 1 times e to the lambda s minus 1. And this is e to the lambda plus mu s minus 1. And this, again, is the generating function of the probability mass function of a Poisson random variable with mean lambda plus mu. And that proves what we wanted to prove. Okay. Right. So this is what I just said. Okay. So let's make this a formal definition. So if x is a non-negative integer valued random variable, then we have a very natural sequence of real numbers where pk is the probability that x equals k, and then the probability generating function of the random variable x is just the generating function of this sequence. So p0 plus p1s plus dot 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 pn s to the n. And we saw the generating function of a Poisson random variable is e to the mu times s minus 1. Fair enough. Another way to look at this is the expectation of a particular random variable. So this is s to the 0 times the probability that x equals 0 plus s to the 1 times the probability x equals 1. This is exactly the expectation of s to the x power, where x is our random variable. So compare this to the characteristic function. Remember, characteristic function was expectation of e to the it x. So again, it was the expectation of an exponential in x. Here there was the imaginary number, which makes it different than this probability generating function, but in a lot of ways they're similar. Okay, so we saw this example. Okay, and a good exercise to check your understanding is to find the probability generating function for some other simple discrete distribution. So Bernoulli with parameter p, that one should be quite easy. Binomial NP, And again, here you can use the fact that the sum of independent random variables, their probability generating function is a convolution, and then a convolution is a product. So use convolution rule. And then compare this to the convolution rule for characteristic functions. It's also a product. And then you can also try geometric with parameter p.